is going to be on Perovskite-based subwavelength metasurfaces for room temperature exciton-polaritons. Hai Son, you can start whenever you're ready.
Hello, everybody. So thanks, Chairman, for the introduction. Do you hear me well? I have some issue with my microphone lately. So it's, hello?
Yeah, it's okay. We can hear you.
Yes, yes. Thank you. So today I present you another system to make exciton-polaritons, a little bit different to what we have heard so far. But also we will see some similarities. Perovskite-based subwavelength metasurface, of course, for room temperature exciton-polaritons. So most of the work here is achieved by my PhD student, Hai Dong. The analytical calculation has been done by Dario Gerace from University of Pavia, and the perovskite material has been obtained from Emmanuel Denport group at Laboratoire Mécoton. So first, I don't need to go into any introduction anymore because we have heard enough of exciton-polaritons up to now. Just to highlight that if we want to go to room temperature regime to make optoelectronic devices, we should switch into high bandgap semiconductor like TMDs, organics, gallium nitride, zinc oxide. And of course, the target is to make polaritron laser logical devices and electrical injection, as Choi has been mentioned lately. So the textbook polaritron scheme is the famous Fabry-Perot cavity with so much success. Now in this conference, we have seen a lot of engineering polaritron dispersion by actually either etching the Panama microcavity into micropilar and coupling one to the other one, or if we don't want to do some etching, we can engineering the potential landscape by optical potential. But in such regime, with a lot of success, of course, it's still a tight binding physics. And we are talking about the pillar of the size much bigger than the wavelength of light. And the distance between pillar is about 10 lambda. And of course, the height of the pillar is also is very high, taken into account the dielectric Bragg mirror. So we are in microphotonics physics. What happens if you want to engineering polaritons but into the subwavelength scale? So we go to the nanophotonic regime. So here we want to introduce a new notion that we call excitonic metasurface. That means we use a excitonic material, a lattices, but now it's a subwavelength lattices. Now the period and also the thickness of this rod is much smaller than the wavelength of light. So in this regime, we can adventure with a lot of new phenomena like Bow-state in the continuum to study topological charges, polarization vortices in case-space, also the extended exceptional points and from Yark as lately discovered by the MIT group for pure photonic system. And of course, if you can reuse the size of everything, we can go to the blockade regime in a smaller footprint in the nano cavity. I talk about the, for example, photonic crystal nano cavity. So this kind of excitonic metasurface that we formally call here is not something completely new, because if you look into the literature at the beginning of polaritonic devices, when people are still working in gallium arsenide system, is already studied. For example, here when we have photonic crystal polaritons in gallium arsenide, and this one is the lasing, polaritron lasing with the nano cavity. But here is for gallium arsenide, so working only at 5 Kelvin, and when you work with gallium arsenide, you make photonic crystal, you etch the quantum well, and you introduce a lot of non-reactive losses. So that's why the idea has been abandoned for a long time. And recently, with the emergence of TDM-DC, people start working again in this excitonic metasurface by depositing TMDC on top of subwavelength lattices. You can see here. So the strong coupling regime has been demonstrated, and also even the famous Baustedt in the continuum regime, when you can see here in the dispersion measurements, the proteins disappear and gamma point, means the relative quality factor goes up to infinite. But in such a scheme, the light matter interaction between the TMDC and the three modes in the grating here is only via evanescence coupling. So we cannot engineer much and enhance its interaction. To make it best, it should be ideally if you can pattern directly the excitonic material. And of course, we need to choose a room temperature material to have it working at 200K. So what we do in our group is to work with 2D perovskite. So the strong coupling regime with 2D perovskite has been observed with a lot of papers mentioned here in Fabry-Perot cavity. So people see very well the anti-crossing effect. And then what is interesting about this material with respect to the other room temperature material is that recently Daniele group has observed the nonlinear interaction, very strong nonlinear interaction in perovskite-based proteinic devices, and is very similar to the gallium arsenide interaction because it's a spin-dependent interaction, it's an exchange interaction, it's not from saturate of the material, and its order of magnitude is larger than alternative room temperature protein devices. So that's why the 2D perovskite is very attractive to work with. So to make the perovskite metasurface, our first approach is to prepare a low refractive index backbone. Here is a silica backbone that we obtain via e-beam lithography and reactive ion etching. And then we just filtering perovskite inside. So you can see here that we make small rods of perovskite and encapsulate everybody with a PMMA. So we can see that it's like a lattice of a perovskite rod with the period much smaller than the wavelength. Here we have the period about from 200 to 300 nanometer. So here's a square lattice, and I will show you two structures that we call A and B with different period, 250 and 350 nanometer with slightly different perovskite thickness. So first, with the structure A working in S polarization in polaritons community, we have the habit to call this the TE polarization. You can see the simulation of the passive structure. If I take out the Lorentz oscillator of the perovskite, we have the linear dispersion, and it is experimental results of the reflectivity that we observed, the rapid splitting, the upper lower polaritons. So we have here the strong coupling regime, observed very well in PL experiment with the lower polaritons. And our results match pretty well also with the analytical model predicted by Dario Goracci. So here we have linear dispersion, very similar to the guide patterns in waveguide that Thierry presented in the previous talk. So it's ideal for propagating polaritons. Now with the structure B working in TM or P polarization, so the passive modes is a parabolic dispersion, very similar to the Fabry-Perot cavity. And of course, when we observe with the strong coupling regime, I mean, I put exciton inside, we can see the protonic modes and the dispersion. Of course, close to K equal to 0 is still a parabolic dispersion, but we have also the inflection point. So showing that we have really strong coupling regime. So you can see here the group velocity as a function of the wave vector. And when the group velocity goes to 0 at 5 micrometer minus 1 here, we have the inflection points. So it's this one you see is very familiar to the protons in the textbook cavity. But then the same structure looking at S polarization is quite different. So you see here the passive photonic modes is quite complicated, but the interesting one is this guy. So it's not parabolic dispersion, you have two minima. So it's a kind of multi-valley dispersion. So in the strong coupling regime, we observe the upper and a lot of lower polaritons. course, we see also in the PL measurements, and it works pretty well when you compare the experimental measurements and the analytical models. And then in the multivariate dispersion, we have two valley points here. And these two valley points is very attractive. For example, if we want to study Josephson oscillation in K-space. And of course, we have also a perfect test bed to make parametric scattering experiments. If I pump resonantly protons at scale equal to 0, I can expect that it's cast. You have one go to the left and one go to the right to evidence the nonlinearity regime. So we demonstrate that metasurface is very interesting for protonic devices. But then the fabrication method by infiltration is a little bit of based on luck, because it's not homogeneous. You can only do it with a small surface. So we try to push it further to make imprinted excitonic metasurface. So instead of spin coating onto a photonic crystal backbone, here we spin coat the perovskite onto the flat substrate and then taking a mold and print it on top of this. And the mold here, we can use a photonic crystal mold with centimeter square surfaces. So as I show you here, so the mold is this size. So outside is unprinted perovskite. And when we printed perovskite with 2D photonic crystal mold, we obtain here a very homogeneous surface up to centimeter square. And you can observe in the SEM image with different magnification that we have perfectly homogeneous pillar lattices, subwavelength pillar lattices. And of course, the same mold can be reused a lot of times on a different kind of substrate. So for example, this one is perovskite on silicon dioxide on silicon substrate. So we observe the strong coupling regime. Here, PL, reflectivity. When we imprint it on silicon dioxide substrate after 10 times, I did mention here that we did it 10 times and it still worked perfectly. You can observe the perfect match between the two fabrication, and also it matched very well with the simulation. So with this, I go up to the conclusion. We propose here a new platform for integrated protonic device at room temperature. It's a perovskite-based metasurface. And as illustration, we show here how we can engineer room temperature protonic modes in subwavelength metasurface with linear dispersion as guided polaritons, parabolic dispersion like the one in Fabry-Perot cavity, and even Valley dispersion. And to push it further, the concept we propose to fabricate protonic devices by imprinted, so with large surface and low cost. So that can pave the way to make a totally integrated protonic device on chip and on a silicon substrate, CMOS compatible. So with this, I want to thank you for your attention.
Okay, thank you, Hai Son. Very nice talk. And so now we have time for questions from the audience. Yeah, Guillaume has a question.
Yeah, I was wondering, well, I would have several questions, but the first one would be about the line widths of the modes, which, okay, are realized with this technique and for this, using these metasurfaces and so on. How does it compare? I mean, is it very broad or just as usual, I would say?
So there are two line widths. The first one is the radiative losses. That one we can control by designing obviously the photonic modes, or by making bounded in the continuum, or making almost guided polaritons. But then, of course, you have the inhomogeneous broadening is due to the fabrication techniques. So this one, of course, you need to improve to be improved by using a better imprinted machine. So for example, the one that I show here, these imprint techniques, we don't use a real nano imprint machine. Actually, it's the one that people use in our school to make ceramic. So it's not for making nanostructure, but it's still working. So if we use a real nano imprinted machine, of course we can expect to have better levels. But yes.
Yes.
Okay. Thierry has a question now.
Yes, maybe how do you distinguish between a photonic crystal and a metasurface in your case? Can you tell us a bit more about this difference?
Yes, because it's a little bit vocabulary. So so photonic crystal is very broad. You have a periodic system. You have photonic crystal. It can be tie binding and it can be not tie binding compatible. So here we want to call metasurface when the period is much smaller than the wavelength. But of course, depending on community, people can call things differently. So yeah, it's just a way of vocabulary. So because that's all. So here is the subwavelength lattices, it's correctly called.
Doesn't seem to be very deep subwavelength though. So the period is.
The period is about 200 or 300 nanometer, and the wavelength is 500 nanometer. So it's about half wavelength.
Half a wavelength.
Yes.
So
yeah,
because that's still in a regime where people define metasurface, or it's closer to photonic crystal maybe. Because you have.
I mean, yes. So a metasurface, some community even use it with the wavelength is bigger than is smaller than the size as well. So I think it's a question of vocabulary. So people working on mirror resonators, they use also pillar, which is a size comparable to wavelength, and separate it far enough so that it does not interact. So it's when making phase array, for example. So it's, again, I think it's a question of vocabulary. Here, our idea actually is working with λ/2 regime. So we start with the waveguide, and then we pattern the waveguide to make propagating modes couple one to the other one. So this is our approach. So that's why you see a lot of things is λ/2 here, like the period, like the thickness.
Okay. Okay, so we have another question, Barbara.
Yes, I would have a question about the size of the crystallites of your perovskites. So what is the size of these crystals?
So it's a polycrystal. Because we work with spin coating. So in different groups, they can grow single crystal, like the one in Lecce and also in NTU in Singapore. So it's a grow of single crystal perovskite. But then since we want to imprint it, so it needs to be some kind of soft material before going into crystallization. That's why we use a spin coating. But then even it's a polycrystal, but since the pillar is very small, because in general, if you look into literature, perovskite solar cell, polycrystal is about a few micron size. Since our pillar is like hundreds of nanometer size, so each pillar is a single crystal, and it's well shown in the image.
Okay. I don't see further questions, so I think it's a good time to wrap up this very nice session. And thank you all, especially the speakers and the audience.